Okay, Algebra 2 skills number 30, graph transformations. So let's see what's going on with this. First, we'll talk about a parent graph. A parent graph is the simplest graph of a family. So we're looking for graphs basically have no transformations. Okay, an example of that would be the y equals x squared family. And what we have here is this nice parabola that there's no adding or subtracting or multiplying or negatives. And the graph is nicely seated at the origin here for the vertex. This would be an example of a parent graph. We have our shifts, which are a way that you can change a graph. So we'll see what happens here. If you add on the outside, you're going to go up. Subtract on the outside, you're going to go down. Add on the inside left. Subtract on the inside right. And these bottom two might be surprising because you think add would be to the right. But notice that if you add or subtract, the graph is going to move from the parent graph. So let's see some examples of that. So here we're adding. This is an example of adding on the outside. Remember, y equals x squared is that nice parabola. This plus 2, if you remember from the previous slide, is going to make it go up. So here's an example of that graph. Now the blue graph is going to be the same each time. The red graph is the new one. If we add this 2, notice it's exactly the same shape. It just simply went up 2. So adding on the outside makes it go up. If you subtract on the outside, if you remember from the previous slide, you're going to go down. So see an example of that. Again, the blue is the parent. So the red is this graph, x squared minus 2. It takes the parent and it simply moves it down 2. So not only the vertex, every point on the graph is exactly 2 positions lower. This is an example of adding on the inside. Notice that we have parentheses here to show that that 2 is also part of the square. So this is an example of adding on the inside. If you remember, adding on the inside makes it go left. So here's the parent again in blue, and the red graph is this one that makes it go left. And then if you subtract on the inside, it's going to go right. Again, the blue being the parent. Looking at a combination, which is certainly, you can do 2 directions at once. Here you're subtracting on the inside and you're adding on the outside. So that's going to make it go right and up. Right 1 position and up 3 positions. So again, you can see the blue, right 1 position, up 3 positions. It's the same graph. It looks smaller. It's not smaller. It's just that you can only see this small, this bottom half of it. So that's why it looks smaller. If we were to extend the graph, you'll see these parabolas are the same size. Now, another thing that people like to do here, they like to think of this as a coordinate 1, 3. Notice that you change the sign here because we were a little surprised here that this negative makes it go to the right. And there's a reason for that, but for simplicity's sake here, a lot of times we just change the sign if it's on the inside, but we don't on the outside. Okay, so if you see 2 numbers at once, you can think, well, change the inside number, don't change the outside number, and that becomes the vertex. This is the point 1, 3 right there. So that's a shortcut that some people like to use. So we also have vertical stretches and shrinks. Shrinks are sometimes called compressions. A vertical stretch is when you, first of all, a vertical stretch, as we'll see, makes the graph either steeper or more narrow, depending on what shape you have. But that's when you multiply the entire function by a number either greater than 1 or less than -1. Okay, so it'll be a number like 2 or -3 or 6 or -10, just as an example. A vertical shrink, sometimes called a vertical compression, is flatter or wider depending on what kind of shape you have. And that's when you do every other possibility. You multiply the entire function by a number between -1 and 1. Okay, so when you multiply, it tends to affect the steepness or the, whether it's flatter or wider or more narrow. It sort of compresses it in or makes it steeper or less steep. Notice that 1 and -1 are not an option. If you multiply by 1, nothing's going to happen. If you multiply by -1, there is an effect of that negative, but it doesn't affect the steepness or the width of the graph. So let's see some examples here. So again, we have the same family. Let's apply a stretch. So again, it's a stretch if you're multiplying by a number larger than 1 or less than -1. So 2 is larger than 1. The note said that it should get either steeper or more narrow. So again, seeing that the blue is the parent, this graph is in red here, and it definitely got more narrow. Okay, so just associating a number bigger than 1 with more narrow would be a good idea here. Now vertical shrink, remember that's multiplying by a number between 1 and -1, which certainly 1/2 is. The note said it got flatter or wider. So in this case, again, the blue being the parent, you can see clearly the red is wider. That's the effect of multiplying by the 1/2. We also have reflections, and reflections can get a little bit complicated, so we didn't put every possibility in this graph or in this slideshow. But if you multiply the entire function by a negative number, it's going to reflect over the x-axis. And we'll see an example of what exactly that means in a minute. If you just put a negative on the front or leading term, it's going to flip it upside down, but not necessarily flip it over the x-axis. So let's look at an example of that. So here we have, this is not the parent because we're adding 1. We know adding 1 makes it go up, but adding 1 helps us see the difference between multiplying the entire function by negative or just the first term by negative. So let's go ahead and look at the graph here. The blue is x squared plus 1 with no negatives. It's just the parent shifted up 1. If you look at the red, notice the red, you're multiplying the entire function by a negative. So the negative goes with both the x squared and the 1. And it becomes this. So notice that it would be as if you took the blue and folded it over the x-axis. Here's the x-axis. If you made a crease, if this were a piece of paper, and you folded it right here, the blue would land on top of the red if you folded it down. That's what happens if you change the sign of every term. That is, you multiply by negative by everything. Now, if you only put a negative in the front of the first term, it's just going to flip it right where it is. So it's not going to reflect in the x-axis. It's just going to flip it upside down. So you're going to keep the vertex exactly where it is, and it's going to flip upside down. So those are the reflections. And there's also a reflection in the y-axis where you put a negative in the x only, and that gets a little complicated, so we won't worry about that here. Also, to go back a little bit, there is such a thing as horizontal stretches and horizontal shrinks, which again gets a little bit complicated, so we're going to skip that in this video, but just be aware you may encounter those. So one more example, this has a little bit of everything in it. This is again in the x squared family, but notice that you have a negative, so there's going to be a reflection of some sort, a 2, which this is technically -2, but it's less than -1, so you're going to have a vertical stretch. You're subtracting on the inside and adding on the outside. So let's look at that. Again, the same parent we've been seeing, and notice all the changes here. So let's think about all these changes. The negative made it turn, go upside down. Okay, so there's the concept of going upside down. I know it didn't go upside down exactly at that point. That's because of these other numbers, but it has it goes upside down because of that negative. The 2 makes it more narrow. Remember, that's a vertical stretch. If you subtract on the inside, it goes right 3. 1, 2, 3. And if you add on the outside, it goes up 4. 1, 2, 3, 4. And when we say it, we usually focus on the vertex for this particular family. Remember also, sometimes people say 3, 4 here for the vertex by changing the sign on the inside and not on the outside. You just have to also know to make it narrow and flip it.